Well, for a little bit of review and also a very interesting application of magnetic force, and that's the cyclotron. And it's really another one of the many applications of the magnetic force. So we've already looked at the well, what happens to charges in uniform magnetic fields, constant magnetic fields. Uh, the charges will move along circular orbits, and if you remember, that there is a period for the circular orbit, which is 2 pi m q b naught. All these are magnitudes, and t is in seconds. Uh, and then from that you can get the cyclotron frequency, which is this value here, or the cyclotron angular frequency. And what I want to do is apply that very interesting application uh, that was done in the 40s, I believe, by Lawrence, uh, Lawrence Livermore National Lab is named after, in fact. And he produced a cyclotron out of a circular piece of metal, and I kind of think of this as a hollow plate that is circular originally. It's hollow on the inside, and then we cut it in half and separate it, and you can see the hollow in here. Uh, and if I look at that from the top down, well, one side looks like a D, at least from this direction, and the the other side looks like an upside down D. So in any event, the two halves are called Ds, or cyclotron Ds. And what we'll do is we will put an alternating voltage source here. This little circle with a squiggle in it is alternating voltage source, and we'll give it like an AC voltage that comes out of your wall. It's just 60 cycles per second, or 60 hertz. And but in their case, we're going to have one that we can adjust the frequency on, and we're going to adjust it. We're going to apply a magnetic field vertically to this, and we're going to introduce some charges there in the center, and of a given mass. So they're identical charges, we'll assume, and we will choose the frequency that we're going to run this alternating voltage to be exactly the cyclotron frequency for this particular magnetic field, charge, and mass. And now I've got sort of an expanded view of it. And I've spread these out much further than they are, just for illustrative purposes. Also, I put the magnetic field going into the page, and it could be a positive or a negative charge. The positive charges will move this direction, the negative charges will curve the other direction. But one sets it up for, in this case, we'll do it for a positive charge. And I'm going to catch this, or make it, just when I introduce this charge at the center here between the two Ds, I'm going to have it so that this metal plate over here, remember this is all metal, make it usually out of copper or something, and the other side is copper as well, maybe metal plates over there, the two Ds. And I'm going to set it up so that when I first introduce the charge, this side over here is at the negative potential, and this side is the positive potential. And that means also that this whole D is negatively charged, and this whole D over here is positively charged. And as you might expect, this accelerates this particle. This positive charge gets attracted to all these negative charges on the inside of it, and so it's going to move in this direction. And when it enters the field region, I'll just have the field in this region for right now, then it starts to go into a circular orbit. As we know, that charges will circulate in circular orbits. Now its radius will be very small because it starts off with zero velocity, and it just gets accelerated a little bit. Now, once it gets inside here, well, effectively it's like a particle that's inside a conductor, and I know the electric fields vanish inside the conductor. So the only place we expect electric field of any appreciable point is in between the plates. It moves in a circular, in this case a semicircular because it's only this side. I've applied this inward perpendicular to the page, into the page B naught here, and the charge will always be in the plane of the paper. And the time it takes for it to make a half an orbit here, well, I know the total time it takes is a period, which is 2 pi, we got that for a circular orbit, is this. So I know that the amount of time it takes for this to make this half circle to this point is half of that value. And we uh, we know that there's a relationship between velocity in this half circle, the radius it makes, and the period. And so once it hits inside here, its velocity is constant at this. And again, I can get the, uh, the velocity uh, times the time divided by 2 pi is r, and you get some cancellation, and you find what the radius of this circle is. But the whole point is when it's moving very slowly, which this is initially, the radius is going to be small because it's directly proportional. Now, we set our oscillator here so that just as it leaves, and I know exactly when that time is, that's half of a period, which I can compute for a given mass, a given charge, and a given magnetic field. Just as it leaves, the polarity of these two plates switches. So this is alternating, so part of the time this one's negative, positive, part of the time this one's negative, positive. And so when it switches, this positive one becomes the negative, and the negative one becomes the positive in this alternating voltage as it goes across. And again, this positive charge is attracted to negative charge, which is on this plate over here, and so it accelerates across here. So there's acceleration in this gap region, and as a result, the particle speeds up. Now, because it speeds up, v gets faster, and the radius increases. And again, it's in this region, comes over to here in a semicircle, but that's larger than the previous one. It's moving faster. Uh, I know how long it takes for it to go through this semicircle. It's just half a period because that's the constant up here. So half a period, I again switch it back again. So once it leaves this at this point, I switch it back so that this is negative and this is positive. It gets repelled by the positive. It gets attracted by the negative. It again accelerates in this gap region. So its velocity increases. It's going a little bit faster on this side. And I know again, the faster it goes, the higher the speed is, the bigger the radius. And so the radius increases. And once it gets here, you might imagine it switches back, and then it keeps switching. And it does that a bunch of times, many more than I'm really drawing here. Yeah. So ultimately, what you have is this. You have this particle comes in, accelerates across the gap, accelerates, accelerates, it spirals out, accelerates, accelerates, and finally gets up here in this region, and I turn off the magnetic field in this portion up here. There's no magnetic field in the gap region, and so when it hits here, it doesn't continue to curve, but it just goes straight. And I've cut a little window here, and I've got a high-speed beam. So you start off with a particle with essentially no velocity, and after it goes around in this ever-increasing spiral and then comes out, you've got an accelerated particle beam that is ejected at this point. Those then, well, initially you could use them to crash particles together in collisions and study the high energy collisions between particles, charged particles. maybe a proton and then slam it into something stationary, or maybe have two of these so that they collide head on, and look at what comes out. And there were a fair number of new particles that were discovered in just those fashions with the cyclotron accelerator. Nowadays, it's not used much except as maybe a starter accelerator. There's other better methods to get higher energies. Uh, but oftentimes you'll create an initial beam that of relatively low velocity, and then inject that into to another process that will get it up to much higher velocities, virtually to the speed of light, within about as close to it as you would want to get. Uh, the um, the big use for cyclotrons, and I've seen them in all different sizes. They literally they look like a little 2Ds. It's oftentimes you can't even see the separation portion. But some of them are is no bigger in diameter than maybe a watch that you have, maybe about as thick as a wristwatch, and in that fashion. I've seen them larger, maybe oh, I don't know, um, maybe 10 centimeters in diameter, and then I've seen some that were maybe probably a meter or so in diameter. So they're very handy, and one can build them very scalable over that range anyway. And a lot of times they're used nowadays for medical applications. They'll create a beam of protons maybe, and then use that to essentially treat cancerous tumors. Try to fire the protons from these cyclotron accelerators into a cancerous tumor, and kill the cancerous tumor with the collisions with these protons. That's essentially a proton beam or proton therapy that they sometimes talk about. You may have heard that term on television or someplace. Uh, but lots of general use applications wherever you need charged particles accelerated to some velocity. You can actually control it to the speed, how many times it circles, and by adjusting the magnetic field and other things. Um, so very very controllable situation.